In this class, we begin the last part of our Fundamentals of Mechanics course. We begin Module 5, which is titled Mechanical Energy. And in it, we are going to address the concepts of kinetic energy, potential energy, mechanical energy. And finally, we will apply all the laws and principles learned to simple examples as we have been doing. We are going to review first before continuing with everything we have been seeing throughout this course. We are studying mechanics from 2 points of view that address the blocks of kinematics and dynamics that define it. In kinematics, what we did was to describe from the geometric point of view the motion of bodies, their trajectory. In dynamics, we also looked at the study of the motion of bodies, but in this case, what we take into account is to analyze the causes that are changing the state of motion of the bodies. We started this study of dynamics with all the definition and all the laws that guide the definition of the concept of force. And that is perfectly established thanks to Newton's 3 laws. And in the previous module, what we did was to extend this study of dynamics but using scalar magnitudes. Force is a vector physical quantity, and we introduced the concept of work, the scalar quantity of work. Now we are going to continue working with scalar quantities with the concept of energy and focusing on the object of this class, which is kinetic energy. We will start with a small introduction to situate and frame the general concept of energy and different types of energy that we can have. We will approach the study of the theorem of kinetic energy, and we will apply it to a very simple example. In general, we can define energy as the capacity of bodies to produce work or change different states. But if we want to be more accurate, rather than talking about energy, we should simply talk about different types of energy and define each of them in a convenient way. Already in 1847, the German physicist Helmholtz introduced a statement that is considered one of the fundamental laws of physics, the law of conservation of energy. And this law tells us that energy in the universe is neither created nor destroyed, only transformed. We have different types of energy that will be addressed. Here in this course, we will only address the mechanical energy and 2 types of energy that we know well, that is the kinetic energy and potential energy. But there are other types of energy. For example, if we look at this photo of Jota, this photo could actually be seen as a storehouse of energy. What we have in Jota is stored energy that he has received from the sun, for example, solar energy, energy that he has received thanks to the food he has eaten. And that energy has been stored in his body thanks to electrical and chemical transformations. If now Jota wants to use it, he will transform it into other forms of energy through the movement of his limbs. Has produced or has transformed that energy that he has stored in movement in this ball by means of the kick that he has produced. This ball has been put in movement, it has acquired a speed, and it is also acquiring height that is related to one of the forms of energy when it reaches the ground. Different types of energy are being put into play: kinetic energy, potential energy, elastic energy. We are going to analyze these different forms of energy. Beginning, now when our film ends, by the different types of mechanical energy, we are going to make a differentiation between 2 types of mechanical energy: kinetic energy, which we are going to define as the energy that bodies have due to their movement and potential energy. The other form of mechanical energy, which is going to be the energy that bodies have due to their position or configuration. Here we are going to have the 2 blocks of energy that define mechanical energy. Kinetic energy receives its name from the Greek word kinetics, which means movement. And if we observe the movement of Jota in this experience, here what we see is that there is already going to be a change in his state of movement. The skateboard has collided with this brick. Thanks to the principle of conservation of the quantity of movement, we were analyzing what was happening in that impact. And if we make Jota's movement evolve, we see that these little stars are indicating that something has happened with the movement that Jota had. And that is described and will determine its kinetic energy. What happens is that Jota has met the wall, and all its kinetic energy has been transferred to the wall. How? Well, in principle, there is going to be an energy in the form of heat that we can almost feel in this photo, that Jota is going to feel in his face and in the rest of his body, and also part of his energy is also being used to break the structure of the wall. We are going to analyze, and we are going to get to know what is the algebraic expression that defines the kinetic energy. Starting from the relationship that we have between work and energy, what we are going to do is to start from the algebraic expression that we were seeing in Module 4 for the work, and that work we calculated as the integral between an initial state A and a final state B of the scalar product of the force by the displacement. That was occurring in the body. In this experience, we have Jota, for example, that is pushing this box. Jota is applying a force and is producing a displacement. That displacement is defined by the differential vector of r and the force applied by the vector F. This scalar product can be decomposed, as always, from the product of modules of the vector magnitudes by the cosine of the angle formed by the two vectors, the force, and the differential of r. Now, in this expression, if we remember from the previous module, it turns out that the product of the force by the cosine of the angle will define the tangent component of the vector force on the trajectory of the body. Or what is the same, we could then rewrite all that tangent force as the mass by the tangential acceleration that the body has. If we introduce these expressions in my expression of the integral, it is rewritten in this other form, where the tangential force, I can put it then as the mass times the tangential acceleration. That would be the derivative of the modulus of the velocity vector with respect to time. In this expression, if I take into account that I have this quotient of the modulus of the position vector with respect to time, this is defining the modulus of the velocity. Then if it defines the modulus of the velocity, I can rewrite my integral in this way, taking into account that the mass is constant, and I can take it out of my integral, and therefore I would be left with the integral, which we know how to do perfectly well. The integral of the velocity times the differential of velocity, which is nothing more than the velocity squared divided by 2 evaluated between the limits of my integral. Therefore, I am left with solving and separating the two terms that appear to me in this definite integral, a half of the mass times the velocity at point B squared that the box has would be at the final instant, and a half of the mass times the velocity at the initial instant squared. We have here a difference of two algebraic expressions that have the same dependence, a constant 1/2 the mass and the velocity squared. This algebraic expression is precisely the definition of kinetic energy, the mathematical definition. The kinetic energy at a given instant that a body possesses is defined by a medium, its mass and its velocity squared. We see the direct relationship it has with the work. Then, the definition of energy as the ability of a system to do work due to its motion is perfectly clear with this definition of kinetic energy. Its units, due to this direct definition from the work, it is clear that in the international system will be the same key as the work in joule. The theorem of kinetic energy tells us precisely this that we have just demonstrated, that the total work done on a body can evaluate it directly from the variation of its kinetic energy. And we see here that Amanda wastes no time in immediately taking this result with her notes. Let us analyze this important result from an example that we already know a lot about the kinematics modules, and I think it will be very clarifying of everything we have discussed. Let's read the statement and remember it. It tells us that Amanda is observing Jota in one of the basketball training sessions. She notes in her notebook that the modulus of the initial velocity of the ball is 8.48 meters per second and reaches at the highest point of its trajectory 5.44 meters per second. Amanda wants to check that the increase in kinetic energy between the two positions coincides with the work done by the weight force on the ball, which has a mass of 600 grams. She wants to see if the principle of kinetic energy is satisfied. We know that from the analysis we were doing in the kinematics module, we were seeing how the trajectory described by the ball was this parabolic trajectory, and we analyzed the different magnitudes as a function of time of the positions occupied by the ball at all times. We are going to fix as extreme values between the instant, the position A, which is just the moment where Jota throws the ball, and the position B, which is when it reaches the highest point. We see here that we have underlined that instant of the highest point when the height marked by the z component is exactly 4.15 meters, and Jota has initiated the launch when the height is 2 meters. The velocities were given to us in the statement. Amanda knows the velocities of the ball at position A and at position B. If we analyze the work in this case, the work is given by this integral. What force is acting on the ball during all this motion? It is the weight force. The force is then defined as minus mg by the vector that marks the direction in that case of the force, which is the vertical vector, therefore unit vector k. And the displacement is given in the y plane, so differential of y unit vector j plus differential of z unit vector k. When I introduce the force vector and the displacement vector in the definition of work, what I get is this expression for integral, where meg will be constant and I will be left with simply the integral of the differential of z, that is, the difference of values at those two extreme positions, in B and A. If I substitute the numerical values that I have for all these variables that appear here, taking into account that the initial position is for 2 meters of height and the final position for 4.15 meters of height, I obtain that the work gives me a value of minus 12.6 joules. Let's analyze now what happens with the kinetic energy evaluated between those two positions as well. The kinetic energy evaluated between those two positions, I need to know the mass that I know and the velocities in those 2 points that Amanda already informed us in the statement. Substituting the value of the velocities and taking into account the mass, I obtain that the variation of the kinetic energy is also minus 12.6 joules. Then it is clear the theorem of the kinetic energy is fulfilled, the work produced by the forces that are acting during the entire motion of the ball. And evaluated between two particular instants, in order to prove this theorem, coincides absolutely with the variation of the kinetic energy. We have it perfectly proved. We have therefore bounded how to calculate the kinetic energy, and we already know that it will always have the same algebraic relationship to define it. A half of the mass times the velocity squared, and the energy theorem that will always be fulfilled. The work done by the forces that are acting during that trajectory between a position A and a position B can also be evaluated as the variation of the kinetic energy of the system, its units in joules. In the next class, we will continue with the study of mechanical energy. But we will focus on the other form of mechanical energy, potential energy. Until then.